Thank you very much for the invitation and the possibility to come here to Belgrade and present some new or older studies and case studies on natural refrigerants. Thank you to Bega that he was late, so he gave me the opportunity not being late for the next presentation. And I think we start with the first slides. I give you some ideas where I'm coming from. Originally, I run a consulting company for natural refrigerants as a whole, since 25 years now. When we started, we did 95% on F-gases. Now we do 99% on natural refrigerants for the last 10 years, I suppose. I'm also in an association called Euromon. We are trying to bring information on natural refrigerants to the public. We react worldwide. I just skipped through these. You will find it then in the presentation samples. Our members are all over the world, and the newest members since autumn we have members from the US, India, and China. And the next meeting will be in Schaffhausen. And maybe this is interesting for you because in Schaffhausen in June we only deal the question of small applications on natural refrigerants up to 200 kilowatts capacity. So we tackle the questions of hydrocarbons, CO2 and ammonia. If you're talking about natural refrigerants and case studies, I always bring one of the oldest case studies. It's a CO2 plant which was installed in Vienna, Austria in 1904 in a hospital, and it ran almost 100 years till 1997. It is worth to mention that in 1904 the CO2 plant was already used. It came from a slaughterhouse, so the hospital bought it very, very cheap. So the system ran over 100 years. The COP of the compressor steam was 3.36, which is not the worst. And it's worth mentioning that the testing pressure was 200 bar and the working pressure was 60 bar. We are talking now about high pressures on CO2 transcritical compressors. My grandfather was used to test compressors with 200 bars. If we talk about regulations and standards, this is a standard from 1870 how to make a documentation on a refrigeration system. You see it on the other side. It's from 1870. It's original from the CO2 plant, where all the engineers who were working on the plant had to sign. And the last engineer who closed the plant was 1997. He made the last sign on the documentation on the refrigeration system. If you go in detail in the system, you have all these kind of questions we are already dealing now. Servicing the compressor, servicing the secondary loop, service and maintenance. So everything is in there, and this is a standard from 1870. If we also talk about natural refrigerants, and they are new now, this is a handbook, a university book from 1904, where they explain the capacities of ammonia and CO2. You see the small pipework on CO2, the bigger one on ammonia, and where they said, now we can handle the high pressures on CO2, we already can run CO2 systems as well. Now a little bit to my history. While we came to natural refrigerants and charge reduction, you have to go back to the 1990s, 1994. We had a change on R22 in the systems. And in Austria and also in Germany, Greenpeace was sitting in front of supermarkets, and they demonstrated on F-gases and on ozone depletion. So the supermarket got a little bit nervous, and they tried to reduce the filling amount of R22 or R44A. So the discussion was how to reduce it. The first and most easy step was to make a secondary loop. With a secondary loop, you all know you have 3 kelvins of loss on your heat exchanger and you have 2 pumps. So we were looking for a better refrigerant. And the better refrigerant, better than 404A, was ammonia in this application. So it happened by accident in charge reduction for the supermarket chains that we used ammonia. Basically the systems were almost built the same. We had a primer circle with ammonia or ammonia debutylator, the secondary refrigerant as a glycol or as a brine, and then a low temperature circle with 404A, or right now with CO2. And if you see the picture we put here in 2002, because we were not really in the knowledge of using CO2 in a wider range, we used small 404A racks and condensated via the glycol. You also can see the filling amount of the systems. We have 350 kilograms of kilowatts of ammonia capacity, and the charge is 40 kilograms and 0.11 kilogram per kilowatt. So very, very slow charges. The machine is in a machine room, so if there is an accident, there is no harm to any customer. The oldest system is now running since 1994 in the same application. This is another application where we use a mixture of ammonia. Maybe to explain you, if you use pistons or reciprocants, you have a problem to use ammonia air-cooled. So we mix it 60 to 40 with demethylator, and we can run a small ammonia demethylated chiller air-cooled for small supermarkets. With this system, we also do the air conditioning and the heating, and we sell the extra heating to a doctor's office, which is right to the supermarket. So we sell in winter warm water to another office, which makes the system really reliable. In this supermarket, we have a bakery, a butchery, and a normal supermarket chain. The discussion was whether to put 3 systems or 1 system. We just built up a bigger system. You see it's still a small one with 50 kilowatts, but these 3 customers share 1 system, and they just meter out the glycol, how much capacity they use, and then they have a common bill, and they share service and maintenance. Which brings us more efficiency on the system and saves costs to the customers. I already presented in some audiences the first supermarkets on the African continent. Today I want to speak a little bit about the background. Not on the technical reason, but what happened when you implement a new system, let's say, which has never been done on the whole continent. And, actually, the challenge was that the German GIZ wanted to implement natural refrigerants on the African continent in 2 supermarkets. And in fact, it was not done on the whole continent of Africa. So I flew down, I visited 11 days refrigeration companies, had speeches there, we had discussions about the possibilities. One point was using copper in a pipework. This is a speciality to South Africa, that copper is really expensive, and if you have copper outside of your supermarket, it might disappear over the night. Even liquid lines are cut. We had this discussion to use relatively less copper pipework, more in steel or in plastic or in ABS, which is a speciality maybe more in South Africa. But it was important to talk to the contractors how the situation in the country is, otherwise you design a system which is not possible to build. Actually, we did some ammonia CO2 systems. This is a picture of the CO2 rack and the ammonia rack, which was built up in Johannesburg. The system was designed in 2008. In 2008, it was in our mind, it was the only way to go with a small ammonia system and a CO2 cascade system, because using propane 2008 in South Africa might be complicated. You see the CO2 rack. The CO2 rack was for Johannesburg was manufactured funny-wise in Australia. So the compressors went from Germany to Australia and from Australia to South Africa. The ammonia rack was directly manufactured in the city of Cape Town. Here you see on this one picture on the right side, we made a glycol loop, and because they had high problems with copper quality and with theft of quality, copper might disappear over the night, as they said. We did the glycol loop in ABS, pre-insulated pipework. You see that here. It is worth to mention that one of the main problems was that the supermarkets took existing supermarkets, so they wanted to revamp it. And on the first side they said, okay, we close the supermarket for 3 weeks and you can put out your new. When we came to the project, these 3 weeks disappeared, and we did the whole change, even from cabinets and shelves, during the opening hours of the supermarket, during the night and over the weekend. Which is a little bit challenging with a lot of pipe work and putting up ammonia systems. We also changed the place from the ammonia system 3 times, from underground to just a 0 floor, and then we put it upwards. Here you see what I mentioned before. So the guys are making the pipework on the cabinets, and the people below are buying goods, vegetables or milk. We also see these are the CO2 compressors for the site in Strand. One side effect was that we were implementing glass doors on the medium temperatures, which have not been done so many in South Africa. When I visited first, we had shelves, freezer shelf, open freezer shelf without glass doors, 2 meters high, minus 24 degrees. These were the elder supermarkets. Now they use glass doors. We also made the tests with an South African producer, because they have a producer down there for shelves and cabinets. So we had we also made the pressure tests on CO2, which we made like South African do. We put the cabinet outside on the parking place, put it under pressure. South Africans opened some bottles of beer and we sat down and waited. So nothing happened. Pressure tests were successful, and CO2 systems are still without leakages since 2009. Here you see that we were installing even the coils in the butchery, so they were cutting the meat, and on the above the engineers were working and installing the evaporators and coils. And this was the sign. This is not right here. Dear customer, we work for you, so we had put in the shelves on the opening hour of the supermarket. This is one let's say, main point in the side of strength. We did two different systems design because we didn't know how good the heat exchangers in South Africa are manufactured. So we took, on one side, we took a second loop where we condensed the CO2 via the brine, via the glycol. On the other side, in Cape Town, a completely rack was bought with a surge drum and then an evaporator heat exchanger for condensing the glycol on the one side and condensing the CO2 on the other side. This happened also by accident because we get one contractor, and after he signed the contractor, he asked me where he could buy the system. So we bought the system completely manufactured in Germany. The system was brought down to South Africa. 2 engineers flew over, and they made 10 days on training, directly installing, manufacturing the site. And this refrigeration company now has done, I think, 30 or 40 applications, ammonia CO2 cascades, propane CO2 cascades. And the technicians who were working and installing, they said this was the best idea ever because they had 10 days on training with the engineers, and now they know how to install it. So the system really worked out good. The main data on the supermarkets were, and this was the bad situation. They had R22 as a refrigerant, which is not the worst on efficiency, to admit, but they had average losses between 18 and 240% of the total filling amount a year. The funny thing is that they really weighed the bottles they brought in the machine room because they had so many losses. They had a personal weight, so the technician went in with the bottle, they weighed him, and when he weighed out, they weighed the bottles again. So the supermarket chain really had, the supermarket manager was responsible for the kilograms used on the refrigerant. I never saw that again in any country, but it was so expensive, the refilling and the service and the maintenance, so the change said, okay, we make it over, we weigh him going in and going out, and then we have it. So these figures between 80 and 240% are true because they were directly with the costs of the supermarket. We changed the system in an ammonia system, almost exactly the same capacity. We changed a little bit the evaporating temperatures. To be honest, the evaporating temperature right now even higher because we calculated the cabinets -6, -2 on the glycol to reach 0 degrees in the meat cabinet. The South African cabinet producer, he has a license from the Americans, and the Americans have very, very big heat exchangers, not our Europeans ones. So we run the glycol with -3 and also have 0 in the cabinet. These are the other status from Cape Town. As you see, it was almost the same. 80 to 240%. We changed it. Actually, here the capacity was not really known, but they knew the filling amount because they had to pay every year 3 times, 2 times total filling. This was also a side effect on which was not really planned in the original project. There was a startup company which is now, I think they started with 3 persons, they are now almost 40-45 persons. They only collect efficiency energy data out of supermarkets, distribution centers, butcheries, bakery, whatever. Here for the supermarket manager every week gets a report on the efficiency of his systems, independent on the control units they have in the supermarkets. And here they have a band And when the supermarket leaves the band on 10%, they get an efficiency alarm. Your energy consumption is too high. Do something. You have some problem on your refrigeration system. They also have sub programs where they have door opening, whatever. Yeah. But it is really, and you have a tendency on 4 weeks and last week's energy consumption, so that the supermarket manager only gets this information he is really interested in. He is not interested in evaporation temperature or condensing temperature, but he is interested when his supermarket leaves the 10% band on energy consumption, because this directly is in his interest, because this is money. The emission savings originally, this was not done by me, it was done by the GZ and the Environment Department. We meted out first the R22 plants, and then we meted out the ammonia CO2 cascades, and we had an energy saving. This is Cape Town on 19%, and in Johannesburg we saved 26%. Which is funny because the Johannesburg system should be not so good than the Cape Town system, because we have a second circle inside and we do not condense directly the CO2. I think it's also a matter of running the system, because the market manager changed in a while, and then how they close doors, how they put goods in cabinets and whatever, so it has a great influence on it. So the idea was to implement the first supermarkets with natural refrigerants, and it really came out that there are a lot of other tasks to do when you implement the system. It's not bringing just a fridge to South Africa and plug it in. So we had a lot of different challenges which came out of the project. First, as I said, installing the new systems to the supermarkets were open. Then installing the systems after changing the machine rooms. So we changed the positioning of the machine rooms 3 times. In Cape Town, the ammonia machine room is in a height of 6 meters, and on the other side we have a school and kindergarten, so we had to take care of it. Then we had to check the shelves and cabinets with respect to CO2, also respect to glycol defrosting and energy efficiency, so we did a lot of work for the cabinet producer. The next point was we set up the system according to the EN 378 standard and according to the South African regulation and standards. The systems were checked by TÜV Germany according to EN 378. We did first time in South Africa a full documentation of the project, risk analysis, that all schematics were on site, that the schematic was on the wall in the machine room, etc., etc. I think you know all it very good. The old documentations on the sites were 3 pages, the company name, the refrigerant, and the emergency number where you phone when something doesn't happen. The documents, the projects are fully documented. We set up a service and maintenance system where we set up when there is an alarm, how many hours they have time to come, what service things they have to be done. We also set a monitoring system on energy consumption and on temperature alarms. And what we did in extra was calculating the secondary loop system, dimensioning vacuum, deaeration, pumps. In South Africa they already had secondary system, but with a lot of corrosion in it, which really did not work. So we did the calculations with the manufacturers. We worked till Friday, and on Saturday we sat and did dimensioning and calculation in the offices. So we calculated the pipework, the valve stations with them. and which came out some thoughts to the efficiency. Originally, we had a system with a brine calculated, and we made an alternative with propylene glycol. And I just did a short calculation on a 20 kilowatt heat exchanger using propylene glycol or a brine. And if to be honest, you see here you have the kilowatts, then you have space, reserve space on the surface. So if you take the same coil and you calculate with propylene glycol and brine, the capacity of the coil goes up. The pressure drop is lower, the surface is the same, the weight is the same, and this is the accident weight, which is calculated. You have to calculate not only the coil, you have for the statics, for the engineers, for the architecture, you have to calculate an accident weight. This is the weight, the coil, plus the refrigerant or the brine, plus the ice on the fins. So, and you see, if the coil has 212 kilograms, the accident weight the architect of a supermarket or a distribution center needs is 581 kilograms. And if you go to efficiency, and you see in the third column, I calculated another coil, not the same coil, and it is a little bit smaller, but you have your accident weight is not 580 kilograms, it's 280 kilograms, and the costs are minus 25%. So it is on evidence which glycol, which brine you use, which concentration you use, and how you are doing your pipe work. The last example, which is done in Germany, it is a distribution center. Distribution centers, I have here I have the main data. So for 4,500 square meters on vegetables, dairy 4,300 square meters, meat 1,500. Freezer rooms 1,100, freezer boxes for the boxes to deliver the goods to supermarkets. So in total 11,000 square meters. The main idea was the customer said only natural refrigerants, no ammonia outside the machine room, in case for their workers there, and already also for insurance when you have a leakage, when you have your goods stored there, that nothing happens. The filling charge must be lower than 3 tons according to the German regulation and standards. They didn't want an additional heating system, no air conditioning system, no additional water heating system, and they wanted to monitor the system in a total. And these are the main data. So there was 2 megawatts on ammonia, about 560 kilowatts on CO2, an ammonia heat pump of 520 kilograms kilowatts, a 2-stage CO2 heat pump, where you see the evaporators on the roof, a heat recovery system, 800 kilowatts floor heating, 400 kilowatts defrosting, and a small air conditioning system with 140 kilograms. These are the rooms. The rooms are about 80 meters high. We used to use for the CO2 in the freezer room, we used to use penthouse coils. One gangway is about 70 meters, and here you see the penthouse coil. These are smaller CO2 compressors, so one is 175 kilowatts each. This out of the machine room, one hard point. You have the ammonia surge drum, the CO2 vessel, a CO2 emergency cooling. If the ammonia system stops, we cool the CO2 vessel with a small propane unit. And on the back side, you see the heat exchanger for the glycol system. These are some thoughts. pipework in plastic for glycol is used or not used. This is a 3.6 megawatt pump station for a vegetable store, and you see all the standings, everything what is in here is made of plastic. Because of corrosion service, you just clean it and everything is clear. So, coming to the environment, I don't know if these figures are really exact, but ammonia is the only double zero refrigerant. I think you always should bear that in mind. Thank you for listening.